Now that we've dug into the frequency response a little bit, I'd like to sort of talk about how we interpret the frequency response. In particular, how we talk about different types of filters. We've seen low-pass filters before, but also bandpass filters and high-pass filters, and so on. So we'd like to be able to understand the frequency response of different, what I'll just call bandpass generically filters, and explain how different filters can be used for different applications, right? So the name of the game right now is to be able to sort of succinctly describe what are filters doing. And what do you mean by what are they doing? So when we get to Fourier transforms, we're going to talk about how signals can be thought of as being made up of different frequency components. And so we actually, when we say what is the system doing, what we mean is what is the system doing to components of the signal at different frequencies. And this all comes back to the fact that complex exponentials are eigenfunctions of LTI systems. So remember, the context is that we have some cosine omega naught t. This is going into a system h of t, for example, and what you're getting out is the magnitude of h of j omega naught times the cosine of omega naught t plus the phase of h of j omega naught. Right, so we have this magnitude and this phase, and what we're really talking about here is the magnitude of the frequency response and what it means for these sinusoidal inputs at different frequencies. So if the magnitude is greater than 1, then frequencies are getting amplified, right? So that makes sense. Essentially, we're saying the gain of the system is bigger than 1, or the gain could be less than 1, in which case signals are attenuated. The interesting case that we want to look at is cases where the magnitude is approximately equal to 1, in which case the cosine that comes out is basically the same cosine that went in, maybe possibly phase shifted. And that's what we mean when we say a frequency is passed by the filter. So a low-pass filter passes low frequencies, that is, it sends them out with a gain of 1. Now, of course, if it sends it out with a gain of like 3, you can always put a gain of 1/3 to get that 3 down to 1. So really, we're talking about how flat is the frequency response. And if the frequency response is flat for a certain range of frequencies, then we're saying those frequencies get passed by the filter. And the other option, of course, is that the magnitude of the frequency response is close to 0, in which case those frequencies are being rejected or blocked by the filter. So when we talk about filters, we usually talk about blank pass filters, where we can have band pass or low pass or high pass filters. So what do these things mean? A low pass filter essentially passes low frequencies, so the gain is 1 at low frequencies. So we have a picture that looks like this, and this is magnitude of h of j omega, and then it kind of decays off. Right, so that's a low-pass filter. It passes the low frequencies. Here's 1, and the high frequencies after the cutoff WC. So here's WC. The magnitude should trail off, and hopefully, in fact, get down to 0. A high-pass filter, on the other hand, has a magnitude that's 1 for high frequencies, but at some omega c and below, it starts going to 0. So that's a high-pass filter. A bandpass filter is one which has magnitude kind of close to 0, then it's kind of flat near 1, and then it goes down again. So this is 1, right? And then we have two other types of filters we can talk about. One is band reject filters, so basically it's the opposite of a bandpass filter. And then we also have what's called a notch filter, which is basically flat, gain 1, except for like at a tiny frequency we get one frequency we get a sharp decline, and say this is the omega n. This is the notch filter. Right, and so these are the different types of filters that we can have, that we talk about when we talk about filter design, and we want filters which have nice properties. Like we'd like this is what is called the roll-off We want this roll off to be fast. We want this gain to be pretty flat, and you can't have everything all at once. So this is why we have all sorts of different filters, and filter design is a real problem, a real task that you have to solve when designing systems. So let's look at a couple of examples. The first we'll look at is a low-pass filter. We saw a simple low-pass filter before, a third-order low-pass filter, but this is a sixth-order low-pass filter with cutoff frequency 4. So what we can see is that much like we saw for the 3-pole case, these poles are arranged in a kind of semicircle, and that's because if you examine the impact on the frequency domain, the imaginary axis here, this frequency thing, these are kind of focusing well enough to take this low frequency band and kind of make sure that all of this is pulled up to be close to 1. In fact, you can see here it's actually equal to 1 up until the cutoff frequency, which is this is 1, 2, 3, 4, so close to 4, which is like here, and then it starts sharply decaying downward. So over here you can see the last pole is close to 4 at +4 and -4. So this thing is going to be flat all the way up to about here, and then it's going to start decaying after that. So if you think about the rubber sheet, you have this sort of semicircle of poles, and that's pulling the sheet up to almost a pretty much constant level between -4 and 4, and then it lets it decay off after that. This discontinuity that you see here is actually not a discontinuity, because this is -180 and this is +180. So this is actually this jump here is not really a jump at all. So this is a low-pass filter. So what about a high-pass filter? So for our high-pass filter, what we do is we again see that we have this this semicircle of poles, but now we have a 0. We have this 0 that's right here at 0, and that is going to cause the thing to be flat and kind of 0 over in this neighborhood, and then it gets pulled up at frequencies after that. So we see here, it's high for frequencies sort of above 2 over here, and then there's this decay at low frequencies. So at low frequencies, this thing is approximately equal to 0, and then this for high frequencies, it's equal to 1. So this is a high-pass Butterworth filter, and we can get that as an 8th-order high-pass Butterworth filter with cutoff frequency 2. It's high-pass and is in the analog domain. And again, these look like phase discontinuities are not really discontinuities at all. It's just a product of having the phase be wrapped essentially between minus pi and pi, or minus 180 and 180. So now we can look at a bandpass filter. So these are bandpass filters. So rather, this is a bandpass filter. So for a bandpass filter, we need to have our poles kind of arranged in such a way as to kind of pull things up here and pull things up here. It's not quite a semicircle anymore. And then we need to make sure that the low frequencies are still equal to 0. So again, the low frequencies are going to be equal to 0. Then we have this pass range, and this pass range is going to go from 0.5 radians to 2 radians over here, and then we get this decay off for higher frequencies. So this is how you would do a Butterworth filter for bandpass filters, and you see we have these, again, not real discontinuities in the phase that happen over here. So this, you can see now, the design of a bandpass filter is significantly more complicated than a low-pass or a high-pass filter, and that's because we have to have these two sets of poles. Remember, they're occurring in conjugate pairs because we want a real filter, so the poles appear in conjugate pairs, but we have to have, they have to be arranged in this kind of weird, not quite a semicircle way in order to get the bandpass property. So now we can look at a band stop or a band reject filter, and here it's actually going from zero point 0.5 to 2, so zero point 0.5 radians to 2 radians. It's a band stop filter in the analog domain. We get our numerator and denominator, and then we can make our transfer function. And if we look at this band stop filter, it looks even weirder than the band pass filter. Now we have a bunch of zeros, and this is actually like multiple zeros, all centered at -1 here. And then we again have the same sort of not quite a semicircle arrangement of the poles. But this is going to cause the band stop filter. The band stop filter kind of it looks a bit like a notch filter, but it's you can think of all of these gains as being pretty small. So the 10 to the -5, 10 to the -10. So it's basically stopping all the frequencies outside this range where it's passing them. Low frequencies get passed, high frequencies get passed, but this little range here, which is a modest range between 0.5 and 2, this is getting rejected by the band stop filter. And again, we have all of these not real discontinuities in the phase. So we've seen how to design Butterworth filters, using MATLAB basically, and they have closed form expressions. I mean, there's an equation obviously that's being used by MATLAB to spit out the Butterworth filter, but I don't think it's quite insightful to go into that right now. It's better to get a feel for it by looking at what the pole zero diagram looks like. Of course, this leaves a bunch of things that we still want to know about, like, for example, what do ideal filters look like? And we can think of it as like, an ideal low-pass filter should look something like this. An ideal high-pass filter should look something like this, with a straight edge cutoff, right? And in reality, real filters have so if we have a low-pass filter, it's going to have a little bit of wiggle over here, and then it's going to have a little bit of decay over here. And so we want to know, what is this width here? We want to make this small. We want to make this ripple, this vertical direction, also small. And so we have a bunch of design characteristics. This thing which we call the roll-off should be fast, right? And that means that this time to get to this time to get to something really close to 0 should be small. And designing all of these, first off, just designing them on paper using a pole zero diagram is a little bit complicated. Then trying to figure out how to implement them in a circuit is also a little bit complicated. So, a lot of the filters that we look at in filter design now are actually designed in discrete time for discrete time processing of continuous time signals, like we saw a little block diagram of that before. This is kind of the modern paradigm for doing a lot of the signal processing. However, there are cases where you have to design analog filters, especially in some sorts of mechanical control systems, and also in RF or high frequency applications. And in which case you have to deal with this analog filter design. But what I want to introduce really here, and what I want you to take away from this, is the idea of these different types of filters: bandpass and low-pass and high-pass, and something a little bit about what the difference is between, say, this low-pass filter here, this ideal low-pass filter that's given by this essentially rectangle function. And remember, this is the omega axis. Versus like what you actually see in reality, this kind of slightly messier filters which might not have perfect characteristics. Finally, in terms of implementation, there's all sorts of trade-offs in choosing these filters. It's more expensive to design a higher order filter. More poles means like more circuit elements. So there's trade-offs in choosing the filter order and terms of circuit complexity and energy dissipation, and maybe some other design constraints like the circuit complexity, but there's also layout issues. So there's a lot that goes into filter design, and in fact, if you take a class later on where you actually study filter design, you'll see this in more detail. But that's the kind of thing that I wanted to bring up, and we'll talk more about ideal filters, especially when we talk about Fourier transforms, and they form a good abstraction to design real systems, especially like things like communication systems.